All right, so we'll give folks a minute to finish signing in. In the meantime, as you log into the webinar, please take a moment to introduce yourself. Let us know your name and your firm through the chat function at the bottom of the window, and we will get started in a minute. So again, as you log into the webinar, please take a minute to put in your name and your company in the chat function so that our speakers know who all of our attendees are, and we will get started in just a minute. All right, so welcome everyone. This is Erin Donovan, Interim Director for the AIA New Orleans. Thank you for joining us today for this webinar presented by our professional affiliate members, Construction Specialties. Today we will be hearing from Charles DiGisco on the topic Louver Innovations, Advancements in Rain Defense. And just a note up top about the setup for this webinar. So all of our participants will be muted, but you can use the Q&A function to submit questions to the presenters. And you can also drop a question in the chat function at any time if you have an immediate question that you would like answered. We are a small team, so unfortunately we can't really intervene in any IT issues, but if you do find that you're running into trouble with Zoom, just take a moment to go back through your email, find the Zoom call-in number, and that should get you audio access to the webinar. On the agenda for today, we'll be hearing from Charles DiGisco. We'll have a brief question and answer session at the end, and then we'll close out with some upcoming events from the AIA New Orleans. Charles is the Business Development Manager, Louvers, with Construction Specialties. He works to provide engineered solutions and specifications to architects, mechanical engineers, facade consultants, and to stakeholders in the glazing, building, and development market. DiGisco helps support Construction Specialties' national network of independent sales representatives, inside product specialists, and other product experts. Charles has authored 5 AIA-approved CEUs over his career and is an AIA-registered provider and RCEP-certified presenter. His professional experience includes over 20 years of business and sales leadership in the industrial, commercial, and construction markets. And Charles, we'll turn it over to you.
Good afternoon, everyone. Everybody safe and sound? You have to pull your screen down, right, Lauren? Or Aaron?
You should be able to share immediately from your screen, but let me know if you run into an issue.
No issue.
Great.
So let's reduce that. And okay, everybody can see the screen, I hope. So good afternoon. My name's Charles. I've been with Construction Specialties exactly 20 months. Today, you are going to be presented an AIA continuing education course, and the title is LVR 200, Louver Innovations, Advancement in Rain Defense. This is an AIA continuing education program, Construction Specialties overview with focus on architectural louvers. And you can see a couple of images on this screen here. This is the Oculus at the Transit Hub in New York City on the grounds of the old World Trade Centers. And this is the Freedom Tower on the right that you see in the image. Construction Specialties is a registered provider with the American Institute of Architects continuing education system. You will earn credit on completion of this program. Our provider number is J144-03. This program is registered with AIA CES for continuing professional education. As such, it does not include any content that may be deemed or construed to be an approval or endorsement by AIA of any material of construction or other method or manner of handling, using, distributing, dealing in any material or product. Questions related to specific materials, methods, services will be addressed at the conclusion of this presentation. So, what will we learn today? We're going to have a good understanding of architectural louver types, their availability, where to use them, and the conditions where louvers are specified. You will hear AMCA. That acronym stands for Air Movement Control Association. And BSRIA, B-S-R-I-A, is an acronym for Building Services Research and Information Association. Mostly today, we're going to be dealing with AMCA certifications. Knowledge of louver performance and terminology. Free area. This is very familiar to you, I'm sure. You'll often hear 50% free area. We will deal with the pressure drop and how that affects, or how pressure drop is affected by free area, and what pressure drop means to the mechanical system. Water penetration, very important. I will explain that in detail. And then, of course, very typical in your part of the world is wind-driven rain rejection. We'll learn typical louver integration options into your building, various typical conditions, and along the way here today, we're going to develop a more comprehensive understanding of louver products and their place on buildings. So, let's get started. Louver aesthetics is a very major part of the design of a building envelope. This is driven 100% by architects. The architects decide what it's going to look like, where it's going to go, and how it's going to be installed, and what color it's going to be. If you are outsourcing your MEP, FP to a mechanical consulting engineer, you will then be tasked with air take criteria. Air intake criteria is the principal function of a louver system, right? So air from the outside passes through the louver system, stops the water, and then just the air passes through the other side. So aesthetic, 100% architect driven. Air performance, this is in collaboration with the mechanical engineer. And water performance, keeping out wind-driven rain. We're going to talk about that very shortly, why that is so important to the mechanical engineer. On the interior of the building, a louver can serve two functions as well. One is to allow air to pass through the louver system, leave the interior of the building, and the other is to facilitate noise attenuation or noise decay, right? Sound attenuation properties of a louver really become important, especially if the louver is at grade. So a little bit of history. In this image on the right, you see that the blades are quite wide. The face of the blade is got depth to it. The spacing or the free area between the bottom of one blade and the top of the blade beneath it allows a lot of air to pass through. This is free area. So this is an older design, the J style, the Z style. These are very, very good airflow, very good free area, but they offer little to no rain defense. So any rainwater that hits the face of that blade, the widest part that we're looking at, for the most part, gravity will pull it down and away from entering the building. But only the rain that hits the face of the blade will drain off it. Back in the late 80s, you started to see different extrusions that now had a drain in the front, okay? So the conventional thinking is, well, if I have rain hitting the face of a louver blade, and it gets collected and drained off by the design, well, then I have excellent water mitigation, and I've pretty much stopped the entrainment of water in the building. Not necessarily 100% accurate, because the only water that will drain off the face of the louver is all that the drain will catch. Okay. So now the design of louvers is improved dramatically. So on this image on the right, if you can look very closely, you see you have a chevron style blade, and there's a little hook that you see at the top of that blade. There are better images coming up, but the purpose here is you have blades that are closer together, and you have part of the extrusion that's capturing any water that dares to try to make its way into the inside of the building. Okay, so I'm going to go back for a second. This is the older style louver design, wide facing blade, a lot of space between the bottom of the top blade and the top of the blade beneath it. And then we have this. So you can see by the very nature of this orientation, horizontal orientation of these louvers, we have reduced the amount of space that water can pass through. So I'm going to stop here. We're going to talk about why managing water with a louver system is so important. Back in the day, they used to design a plenum, right? So quite frankly, it didn't really matter how much water entered the interior of the building. It fell to the plenum, to the space, right? And drained off. But as buildings became much more efficient and air handlers much more efficient, and the space that a plenum took up was now used for mechanical systems. So now we needed to stop the water from entering the mechanical system. The first space in a mechanical system that water comes in contact with is the filter cartridge, or the filter cassette, or just the filter. So this is the first point where water being introduced to a filter can create pressure drop, because as the filter gets wet, any dust, airborne dust, now turns to mud on that filter and makes the air handler work harder to pull the same amount of air through it. This is why mechanical engineers do not want water entering their mechanical system. Next, extreme weather. And we all know that you have plenty of that down in your part of the world. So, two numbers that I want you to remember. AMCA 540. 540 equals impact resistance. So the impact resistant louver was born after Hurricane Andrew in 1992 in Miami-Dade County. So the building codes changed, and the consensus basically was, we don't want a hurricane making building materials become airborne and become part of the problem. And from that came what they call TAS. TAS stands for Technical Application Standards, along with NOA, Notice of Acceptance. So when you're specifying Dade County certified louver systems by any manufacturer, you will always see the requirement of Notice of Acceptance, NOA, that is an actual number. And you will see AMCA 540 impact, right? So if something hits the louver does not come apart. And then AMCA 550. AMCA 550 is designed for wind loads up to 170 pounds per square foot and wind in excess of 110 miles per hour. So now you have a louver system that is virtually stopping all water entrainment to the interior side and can also withstand the impact of a piece of wood, a limb from a tree, some other building material that might come apart. If it hits the louver is staying in place. Okay, so we have some choices, right? When designing a louver, we have to consider rain defense, right? We just saw a louver system with the blades very close together and that little bit of a hook. You're going to see an image shortly, which we'll talk about. Free area, which is the amount of air that the air handler is requiring. So it's space between the blades through which air can pass. Pressure drop. In the very design of a louver system, by the nature of the blades being so close together, you will have less free area. And if you have less free area, you will have a drop in pressure. We're going to talk about this a little bit more in a moment or two. And then, again, your part of the world, there are louver systems that are designed specifically for extreme weather. AMCA 540, meaning they resist impact. AMCA 550, meaning that they're tested and certified to wind loads of 170 and mile per hour winds up to 110. And then there's the design of the louver itself. Okay, so if I increase the size of a blade, let's say from 5 inches to 7 inch, the depth of that louver increases the same. So if I have a 5-inch blade, I have a 5-inch deep frame. If I have a 7-inch blade, I have a 70-inch deep frame. And a 9-inch, obviously, a 9-inch depth frame. And then off to the right, you see a couple of model types. Now, we're bordering on a discussion of aesthetics here, 100% architect driven. And we're going to talk about this in another couple of slides as well. So you have two choices. The first choice is you can have a horizontal orientation, or directly behind that, you can see a vertical orientation. So those are a couple of choices that you can make. I don't want to give away too many bits of information just yet. So we talked about AMCA. AMCA is an acronym for Air Movement Control Association. They are a third-party independent testing and certification laboratory, I believe in Arlington Heights, Illinois. AMCA is testing and then certifying, but not all louvers by all manufacturers are tested and certified. Some are just tested. So in your specifications, if you call out for an AMCA 540 or an AMCA 550, you are going to get a louver system that has a AMCA label on it saying that it is certified to those specifications, right? AMCA tests air performance, and they test water performance, specifically wind-driven rain. So those are the labels. You will see very often water, air, and wind. The label itself is actually blue and yellow, and most always in the specification, when it's designed, when you write the specification, you will say AMCA 540 or AMCA 550, and that label will be on the frame of the louver system that's delivered to the job site. So a few minutes ago, we talked about Miami-Dade, and I spoke briefly about NOA, Notice of Acceptance. So these numbers here are tied specifically to Notice of Acceptance and Technical Application Standards. Okay, so product 21658 and Notice of Acceptance means that they accepted it's been tested. These are part and parcel to the specification when you move into Dade County, Miami-Dade County louver systems by any manufacturer. So let's talk about air performance. So you're probably saying to yourself, how many times is he going to tell me about free area? Well, it's important. The free area is the opportunity for outside air to pass through a louver system to be picked up by the cubic feet per minute draw created by an air handling unit. So in this illustration, you see these two diagonal lines and the red letters, 50% open free area. So the bottom of the top blade, that distance to the top of the blade beneath it, that is your free area. So a little bit of a dilemma is created. So the mechanical engineer may specify to you that you need to design a louver system that has 50% free area. Okay, so if you do that, you can see in this illustration that the air is going to flow very freely in between the two blades. So you're probably saying to yourself, and by the way, you're correct. You're probably saying, well, wait, Charlie, if I have that, aren't I allowing rain to get to the other side? The answer is yes. Okay, so free area is important. Managing rainwater entrainment is also important. You'll see in a second. All right. So is 50% free area always 50%? So you could look at this picture, this image at the bottom, and say, oh, I'm not understanding this because I have one louver that has 39% free area, and then the one right next to it has 50. What's the difference? Great question. The louver on the left, you can clearly see you only have two spaces, two free areas in that louver system, right? The amount of blades has a direct relationship to the amount of air that can pass through a louver. Case in point, look right to the right, the louver system in the middle is a 4 foot by 4 foot high. There you have 1, 2, 3, 4, 5, 6. You have 6 areas for air to pass through that louver. So the taller the height, the more free area you have. In the 8 by 8, if I'm not mistaken, there are 13 blades. So there is 13 spaces in between the blades for air to pass through. So now you're going to say to me, well, wait a Charlie, if I just take that 2 by 2 and I just make it the entire side of my building, is that not enough free area? Well, the answer is no, it's not. Because even though I installed that 2 foot by 2 foot ribbon of louvers across the entire elevation of a building, I still did not increase the height of the louver, the number of blades through which air can pass. So if you designed a 2 by 2 louver, the best you're going to get, quite honestly, you could put 2 by 2 louver ribbon across all 4 elevations of the building, you're still only going to have 39.5%. So I want you to understand, the taller the louver, the more free area. Oh. So now, this is not a trick question, right? You can see what's happening here. So I have the bottom of the top blade and the top of the blade beneath it as my free area. So the air starts out very nicely entering the louver system, but guess what I did here? I created my own resistance. I disrupted the airflow. I created pressure drop. So I start at 50%, but now I have a louver configured in such a way to mitigate water entrainment that I've now created pressure drop and I have less free area. The correlation between free area and pressure drop are connected forever. The less free area, the higher the pressure drop. Okay, this is a slide I was waiting for to show you. This really tells you what it is you're looking at with regards to managing water entering the building. That little hook is actually part of the blade. It is not, there's no fastening device, there's no adhesive. It is extruded as a one-piece blade. So no areas for corrosion, right? In the front, you very clearly see the drain. So you have your chevron design, you have your hook as part of the extrusion, and you have a drain. So yes, air is still passing in between the blades, but it's doing so with increased resistance to airflow. Pressure drop. Measurement of the pressure from one side of the louver, outside, to the opposite, inside. Measures the resistance to airflow across the open louver. Easy enough to understand that. And the amount of air has a direct relationship to the draft created by the air handler. So the air handler has a centrifugal fan inside, and it's drawing air from the outside in to pass across the coil and then into a duct. But they don't want water in the building. They don't want water coming in contact with the air handler. So you go to a storm-resistant louver designed as such. If pressure drop is your concern, or free area is your concern, very simple. All you have to do is increase the height of the louver. You increase the height of the louver, you increase your free area. Okay. We're going to talk about 2 tests that actually lead to a certification of a louver, anybody's louver. Doesn't matter. So this is called the still air test. So at top, you see the water manifold, and then you see these red arrows here, and the water is very gently falling through that manifold like a spring rain with no wind whatsoever. All the way to the left, you see there's an axial exhaust fan, and the purpose of that fan is to attempt to replicate the draw caused by an air handler's centrifugal fan. All right, so you have water coming down gently, no rain-driven, wind-driven rain at all. The louver, a plenum, and then your fan off to the left. The idea here is, in a normal still air condition, how much water is passing through the louver as a result of being sucked into the building, drawn into the building, drafted into the building by the exhaust fan. That is the 500 test, the AMCA 500 test. So you can have a louver system tested to standard 500, but the real question or the real specification for yourself is that it's certified to the 500 test. Okay? Everybody can test, not everybody certifies. Excellent photo. Off to the left, our traditional, if you remember very early on in the presentation, we had wide blades, rain hitting the blade. Whatever hits the face of the blade, probably gravity's pulling it away. But in this illustration, you can see this Z-blade design offers no rain defense whatsoever. And let's not even talk about wind-driven rain. Off to the right, you have a storm-resistant louver. Do you want me to go back? I want to show you that picture again. This louver system right here is that one. In a traditional storm-resistant design, your louver blades will be closer together. They will have that extrusion, or they will have that hook as part of the extrusion. And these louver systems give you the greatest opportunity to stop water entrainment into a building. Okay. So the first test we saw was still air, okay? It was an AMCA 500 test, but there was no wind driving any water against the louver. It was just wind falling, just nice spring flat rain, and then the axial fan off to the left was creating the draft normal in an air handler. In this test, we have 2-speed fan, 29 miles per hour or 50 miles an hour. And at the same time, we're driving rain pushed by the wind, 29 or 50, we're driving rain either 3 inches at 29 miles per hour or 8 inches per hour at 50 miles per hour. So this test specifically designed to challenge the Louver system and its ability to manage water entrainment. That is this test. It is called the 500L99. You will, in your part of the world, you will specify wind-driven rain louvers almost exclusively. Very rarely would you not do that. So this is what the test chamber looks like. So in this larger box, you see an arrow pointing to an orange square, and that orange square is the louver. So what you're doing here is you're taking, you see this cylinder, you're taking wind and you're driving rain, simulating 3 inches an hour at 29 mile an hour wind, or 8 inches an hour at 50 mile an hour wind, and you are driving that water right to the face of the louver. The test is designed to see if the louver will fail and water will enter the interior of the building. This is a very good test. All right. So let's play a little bit. So we talked about J and Z type blades. Then we talked about a drainable blade. And then the best of the best, storm resistant blade. So the standard blade offers virtually no management of water entrainment whatsoever. 28 liters of water per hour is entering the interior side of the building, right? This is a problem for the air handler, I could tell you. So, okay, you say to me, all right, Charlie, can I design a drainable louver that helps with the water entrainment? Well, yeah, you can. Watch what happens. So now only 26 liters of water per hour are entering the interior side of the building. This is still a mess. Then you say, okay, I want storm resistance. And you're going to get it. That is the difference between standard flat-faced louver, standard louver, drainable, and storm resistance. So 2.5 liters of water per hour. That's it. This is a very important, but it's a very simple but very important graph. Now, if I was with you, I'm sure you'd be having lots of questions, but this is the back of a louver, right? This is the interior side of a louver. And if you look all the way down the bottom, you see a straight but somewhat wide piece of aluminum. That is a sill pan. So the idea is that any rainwater that does enter the building without the force of fans or such, this is a typical louver, it drains off the back of the blade and gets collected by the sill pan and then comes out the front or the side. You also see in this picture, you're going to see it again, you see these two little angles of aluminum. Those are the clip angles. That's what secures the louver frame to the CMU or whatever material that we're installing the louver to. Most likely it is CMU. Here we go. Okay. This is a simulation. This is a test, right? This is not a storm-resistant louver, but it's being tested as if it were supposed to be resisting storm, wind-driven rain. You can clearly see we have a disaster on our hands here by how much water is on the back of the blade. We don't want that. Air handlers hate it. So let's move on. Okay. Here, same size. You can see the sill pan down the bottom, that solid long piece of aluminum. You can clearly see the clip-offs, the clip angles, simulating clipping off to CMU. So attached to the frame, clipped off to CMU. This is a storm-resistant louver. The louver previously was not. Hardly anything. This is what we want. So, drainable, Z or J, no water management, no mitigation, entrainment at all. Drainable, a little bit, not enough. Storm resistant, you win. Okay. There are two orientations. We saw a little image earlier in the presentation. We have up top here on the left, we have a horizontal orientation, clearly storm-resistant blades, rain driving against the face of the blade, and none reaching the interior side of the building. Down at the bottom, vertical orientation, lots of blade face for rainwater to come in contact with. Gravity works in your favor and the water doesn't get to the inside of the building. These are both storm resistant, one horizontal orientation, one vertical. Okay, so 1992, Hurricane Andrew, Miami-Dade, very destructive hurricane. From that came Miami-Dade County notice of acceptance, technical application standards. So you can see in the red, you can see the panhandle, you can clearly see your state of Louisiana there, and all storm resistant louvers are specified in these areas. But look what's happened over time. Now it's traveled north all the way up the East Coast, all the way up to Eastport, Maine. And it's traveled west, completely across the panhandle, Alabama, Mississippi, Louisiana, and all the way down the the eastern coast of Texas. This is where we have the most hurricane-prone, high wind situations. We have options. We have AMCA 540, impact, and AMCA 550, 110 mile an hour wind, 170 pounds per square foot wind loads. We have choices. That's what they look like. These are 540, 550 AMCA tested and certified louver systems. You can get these at any manufacturer, but these are the best of the best for storm resistance. No water gets inside. And if something hits these louvers, they don't come apart. So a little earlier in the slide presentation, you saw this FEMA words, and then you saw another slide and a little yellow box. It said FEMA 361, ICC 500. Okay, here we are talking about tornado resistant louver systems. This is 1/4 inch chevron style aluminum welded to the frame. No mechanical fastening here. This is a very high-performing louver system. So what is FEMA 361? FEMA 361 is the guidelines from the federal government for tornado and hurricane. Any community residential safe rooms, more and more you see safe rooms designed, unfortunately, in schools. So sad to say, but the school still needs to get air. Or the Public Safety Administration building, the firehouse, the police station. All of these locations very often will have FEMA 361 written into the specification. So FEMA 361 is the guideline. ICC 500 is the code requirement. And there's another number that you don't see here, and it is ASTM 330. That is the standard test method. So very often, if you're specifying a safe room, you would design to the guideline of 361. It would be built to the requirement of ICC 500, and they would all be tested to the standard of ASTM 330. Those three numbers. So here you have some ideas, right? So the top left hand, we know what that is. That's the J or Z style with a drain. The next one beneath it, in the center on the left, is a vertical orientation louver. Then down at the bottom, this is the first time we're talking about this. This is an acoustic louver system. So the idea here is we are not concerned about rain defense. We are not concerned about airflow. We are concerned about noise decay and how to facilitate it. So the way you facilitate noise decay is you give the noise the opportunity to reach something that will absorb it. All right? This is very evident if you were to go into a brand new room that you just built for yourself. There is nothing on the wall. There is nothing, no furniture. There is no carpeting, nothing. You can hear your echo because your echo is not decaying in the room. But as soon as you introduce sound attenuating materials into that room, you've reduced the decibel. That is the principle of acoustics. So if you design acoustic louvers, most often they will be in generator set rooms. If the generator room is attached to a hospital building, it's an L3 type generator room, which means you have to reduce the noise decibels by 13, minimum. Off to the right, you see a very slick looking louver system that has storm resistant blades, but this time the architect decided, I want color. So that design introduces color spaced out and 100% architect driven. Directly below it, we've seen this before. This is a storm resistant louver. And then below that, you see a louver system, storm resistant, but in this particular illustration, you see a decorative perforated material in front of it. That system is also tested and certified. Okay, so you have some things to think about here. Acoustics, you can add color, you can add something in front of a louver because maybe you don't like the look of the louver. Total 100% architect driven. So we talked about this. This is the non-drainable design. We know that we have 28 liters per hour entering the building with this type of louver system. Drainable. We know with this system, we make only marginal improvement, but we still have 26 liters per hour of water entering the building. And then storm-resistant louvers. Here we have managed to provide no water or opportunity for no water to enter the building. 2.5 liters per hour, if I remember the number was correct. Okay, so there are a few types of louvers. This happens to be a louver system that would be specified perhaps in a hospitality application where PTAC, package terminal air conditioners, are installed, where water protection is not an issue, but high airflow is. There is your illustration of acoustic louvers. So off to the left, the larger circle, what's happening is the noise is passing in between the chevron blades here, and the material, fiberglass, is providing the opportunity for the noise to decay. It's absorbing the noise, all right? Free area, you're not getting much, and you're not getting any rain defense. Here is the most well-designed system, Dade County approved, Florida product approved. Remember, I used those letters, TAS, Technical Application Standards. And then there's those numbers and those letters again. AMCA 550, impact, and, 540, impact, and 550, extreme wind-driven rain, up to 170 pounds per square foot wind load. And then, of course, FEMA, when we deal with tornado applications or safe room applications. Yes, there is such a thing as blast-resistant louvers. These louvers are designed to take a charge of 12 psi or higher at a pulse rate of 7.83 seconds. A bomb. Federal buildings, GSA product, all VA hospitals, standard blast-resistant louvers. They look quite nice in person because the blade is rather robust, and it's a very nice looking louver, but it is extremely strong. 12 psi is pretty high. And any federal building, if there is a Federal Reserve building, if there is a VA hospital, blast-resistant louvers are included, always. Okay, 100% architect driven. You decide how you would like the louver system to look on your building. Keeping in mind that you're not particularly crazy about louvers to begin with. But off to the right, in this beige building, this green louver system, the architect liked the look of exposed mullions, tall, thin sections. But directly beneath it, you see a clear span louver application. And here, there's a very good chance that that louver system is closer to grade and may actually be, even though it's the same color, may actually be a different louver entirely. And then in the center, if the design allows you to, you could draw in louvers right into a curtain wall system. Clean, flush. Off to the left, you see a louver system for the exclusive purpose of hiding what's behind it. 100% architect driven. I shouldn't say 100%. There are some ordinances, especially for rooftop mechanical equipment, air-cooled chillers or cooling towers, where there may be a ordinance that says you have to cover it. Okay, this is what a standard frame looks like. You can see your clip angles clearly in the section cut off to the left. This happens to be a 4-inch Z-blade, not storm resistant. Here is a flange frame design. So you're saying, okay, this is an exterior flange, so I get it. I can take this louver from the outside and I can push it into the opening and it won't fall through the punched opening. There is also an interior flange, which means that the two flange legs that you see on the left side of this image, they are now on the inside. So that design would be for an installation from the interior side of the building, so the louver doesn't fall through the rough opening. Then there is the glazing option. Off to the left, this little illustration here, I want you to take notice to these hash marks that are in this louver, right? Those are actually drains in the left and the right jamb of a louver so water can drain out. And down the bottom, that little square that you see there, that is your glazing pocket, your glazing adapter. In the center, you see a louver, a storm-resistant louver, clearly. And on the right, you see the classic J-style drainable. 100% architect-driven. Glazed-in louver system, except the architect wanted to create this specific look as if they were all individual. So all that is beauty cap. Other than aesthetic, no purpose whatsoever. I always like this slide. Okay, structural silicone glazing, SSG. This very slick, flush, clean. Clearly you can see it follows, the louver installation follows the contour of the glass. Seamed perfectly. In any glazed application, very often, louvers are sent to wherever there's going to be unitizing done. Another example, perfect, architect-driven aesthetic. This is not an accident. The architect looked very carefully about how everything lined up perfectly. Those are louvers that you see on the side of this building. 100% architect-driven. Another 100% architect-driven application. Here, the architect didn't want straight. The architect wanted radiused. So you can see in this illustration, you see the vertical mullions behind these horizontal sections. So the actual louver itself is extruded in a radius designed by the architect. Another application, okay? This clear image that we see here on the right, that is your radiused louver. You determine the degree of the curve. And the image on the left that looks a little brown or tan in the sunset, how it just fits perfectly with the straight louvers. Architect driven. So I'm going to go back for a second. When designing a radius louver, the manufacturing cost increases. When you design a radius louver with a vertical orientation, the cost increases, but it increases less because I don't have to extrude the radius louver blades. All I need to do is extrude the channel in which they're mounted. That happens to be Madison Square Garden on the right-hand side, New York City. Color, louver type, shape, custom. Architect drew it for the manufacturer. Can you build this? Manufacturer said, yes, I can. Another good example of architect aesthetic. For the most part, because of this grille design, you can't see the louver. It's there. If you look to the image in the right here, the photo in the right, you can see that there's louvers behind it. But if you look in the larger photo where it says parking and you look at that tall piece of grille work in front of it, you can't tell there's a louver back there. Perfectly hidden. In this case, the architect drew the design, gave it to a manufacturer. The manufacturer laser cut or stamped the aluminum, brought it back to the architect. That's the final installation. More architect art. Here you have an architect's clear mission to break up the lines, the horizontal lines, or I should say the vertical lines of the mullions in the back with a horizontal orientation, somewhat spaced widely, nice distance in between them, but it definitely breaks up the image behind it. My favorite slide, because I know that there is nothing going on behind this louver. This is completely an aesthetic at the corner of a building. On the left, the architect wanted it to appear as if the blades were floating. But at the same time, on the other side, he seemed, this is all architect design, he seemed the louvers very close. And directly in the middle, wanted to create a very sharp edge, very crisp edge. So the architect designed all of that. Hands it over to the manufacturer, says, can you build this? Manufacturer says yes. That's the result of the architect's work. Again, 100% architect driven. The architect drew this grille, handed it to a manufacturer. Manufacturer laser cuts that, tests it, and then it's installed in front of a louver system. Okay, we saw this image a little bit earlier on. I'm going to speed up a little bit. I'm running over, sorry. So here you have a vertical louver system orientation and a horizontal orientation louver system. In both cases, perforated material directly in front of it. But if you look down very closely to the bottom, you'll see a space of about 2 inches between the back of the perforated material and the front of the louver. So you're probably saying to yourself, Charlie, if I put something in front of the louver, aren't I creating pressure drop? Great question. You're right. You do create pressure drop. But in this case, the manufacturer designed the space between the back of the behind the back of the louver, the front of the louver and the back of the perforated sheet, essentially creating free area. So compensation was made by creating space for air to accumulate. 100% architect driven. If you look at these metal panels here, the darkest ones in the center, or off to the right, I should say, those are louver systems with perforated panel on top of it, fitted right into the metal panel. Okay, more perforated material in front of a louver system, this time installed. This is a penthouse for mechanical equipment, and these are insulated sound attenuation panels. Okay, we've seen this, right? Charlie, I don't like the way louvers look. I need to add color. That's what you get. Off to the left, storm-resistant design. Off to the right, a traditional J blade back in the day. But there are some very interesting applications for this aesthetic. This University of Pittsburgh. Here, I'm gonna go back one. These blades off to the left, those red ones, essentially, when the architect designed this space, mechanical space, he took those blades and he made them in various sizes and put them in selected locations to create that aesthetic. Beautiful. This happens to be in Cherry Creek, Denver, Colorado. This is a bus station, right? So the staggered coloring of blades, and we've added a thin strip along the edge of the louver blade for an LED light. 100% architect driven. Here you have blank off panels behind these louvers. The two dark sections, that is the actual functioning louver. And then to the left and to the right, you have blank off panels painted the same color as the louver. Now, if the blank off was painted black, you wouldn't know which ones were functional and which ones weren't. 100% architect. We have choices here. I should say you have choices. Okay? Any RAL or PMS color or any custom color that you can conjure up. Anything. You have no limit. So right off the bat, you see anodized, no warranty. Well, Raleigh, I want a warranty. Simple. Paint the louvers anodized bronze, and you get a 20-year warranty. 2-coat, 3-coat metallic, of course, powder coat, 20-year warranty, powder coats, custom colors, green, of course, no volatile organic compounds or hazardous waste. If you look at this image to the right, this is to the left or the right, but this is a very close-up view of the hook that I've spoke about throughout this presentation. That is part of the aluminum blade. It is not fastened with any adhesive or fastening devices. It is all one piece of aluminum. And you can clearly see the drain in the front. 10-year warranty. It looks just like wood. And that concludes my portion of the AIA course. I hope you enjoyed it, and I hope you have some questions for me.
Great. Thank you, Charlie. We'll give everyone a moment to type in any questions that they may have into the Q&A or the chat. And in the meantime, I am going to share some of our upcoming learning opportunities. So we have a Friday storytelling event with Angela Wharton. That'll be at the same time from 12 to 1. She is an AIA past president, and she is current president of AIA Louisiana. And then we have multiple webinars coming up in the coming weeks, those first weeks of June. We have an HSW presentation from Schluter, June 2nd, and another presentation from Hahn on June 10th, and another HSW presentation again from Construction Specialties. They'll be with us on June 16th. So please go to our website, aianeworleans.org, listed here if you want to sign up for any of those. We also have our LinkedIn group, our Facebook page, a lot of COVID-19 related resources on our website. And you can always reach out to Lauren or myself via our emails listed here below. And let's see, we'll give folks another moment if they want to share any questions that they have. Charles, David, do you have anything to add here?
No, I wish I could have been with everybody live, but this will have to do for now, right?
It'll have to do for now, yeah. All right. David, anything from you?
No, ma'am. Just want to thank everybody again for attending today, and stay safe out there.
All right. Charles, David, your information, is that included anywhere that folks can reach out to you if they have further questions?
You know, other than my name on your slide and on the face slide, I don't think so.
Okay.
I could fix that easy enough.
All right.
I'll just send you my my information.
That sounds great.
Yes, I could do that. I'd love to.
And have we gotten any questions?
Looks like we do not have any questions.
All right, well then we will go ahead and close out for today, and we, if folks do have questions for you, we'll be sure to send them along to Construction Specialties. Thanks so much for your presentation. We really appreciate it, and thanks to everyone who attended today.
Thanks, Aaron.
Y'all have a
Thank you.
good one.
All right, see ya.
Y'all too.
Bye, Dave.